Welcome back for another video on the polar coordinate system. In this video, we're going to talk about how to find arc length. That is, if you have a curve that goes around, how long is that curve? If you could put a rope along it and measure how long the rope was, what would that be? And we're also going to talk about how to find the equation of a tangent line to a polar curve at a particular point. Now, the tangent line, of course, is always given with the slope of the tangent line being dy dx. So we'll actually have to convert from polar coordinates back into rectangular coordinates in order to be able to write down the equation of the tangent line. Let's go ahead and get started. We'll look at arc length first. I'll share my screen with you so you can see the notes. So again, we're going to be taking a look first at arc length. So we're talking about how long it is along a particular curve from some angle measure to some secondary angle measure. Now, we talked about arc length before in section 7.2 when we were looking at parametric equations. So let's kind of remind ourselves of what arc length is and what it looks like. Now, in the rectangular coordinate system, you have two equations for arc length, depending on whether you're integrating with respect to x or integrating with respect to y. So the one on the left is the integral to integrate with respect to x. This is the normal one that we use most of the time. This gives us dy dx underneath the radical squared plus 1. Take the square root of that and integrate from x equal a to x equal b. If the equation is better written as x equals some function of y, then you can integrate with respect to y, but the equation is very, very similar. In this case, though, we take dx dy, the derivative of x with respect to y, square that, add 1, then we take the square root of that entire expression, and then we integrate from y equals c to y equal d. And this gives us the two different equations that we have for finding the arc length in a rectangular coordinate system. Now, the fact that we need two equations, one with respect to x, one with respect to y, should let you know that this is not a trivial thing to do in the rectangular coordinate system. In the parametric system, we saw that the equations, when converted into their parametric form, both the integral with respect to x and the integral with respect to y, both simplified and became exactly the same integral. So when we find arc length for a parametric curve, we find that we only have one formula. And that formula is the integral from t equal to a to t equal to b. These are parameter values of the square root of dx dt quantity squared plus dy dt quantity squared, and we integrate with respect to t. So we found that with the parametric curves, this formula actually became somewhat simpler in that there's just one form and you're integrating with respect to t. Now, in many ways, we can consider polar coordinates to actually be parametric equations where instead of using t, we're using theta. So r becomes a function of theta or t. And that way, we're going to find that we're going to have very much the same formula. So now we're going to adjust the formula to be used with the polar coordinate system, and we're going to see that it comes out to be very similar. In order to do that, we're again looking for the arc length. So by arc length, what we're talking about is if I have some curve that goes around like this, I may want to know how long is that curve. What's the length of the curve if that's something in the polar coordinate system? Now, in order to adapt the arc length formula from the parametric equation to a polar curve, we need to use the equations x equal r cosine theta. We know that from the definition of cosine as the adjacent over the hypotenuse. And y equal r sine of theta, again, from the definition of sine theta, which is opposite over hypotenuse. Now, we can also think of r as a function of theta. So sometimes you'll see it written f of theta, And sometimes instead, you're going to see it written as r of theta cosine theta, right? And this, of course, is x. And we can see y is r of theta sine of theta. In this way, we're emphasizing the fact that r is not a constant. R is a variable that depends upon theta. So we've got two things in the expression for both x and y that depend on theta. So when we use these equations, we're actually replacing the parameter t by theta. So we're looking at it as if it were a parametric equation, but with t replaced by theta. And in order to find the derivatives, dx dt, dy dt, we instead compute dx d theta, dy d theta, right? So this is exactly the formula that we had up here for our parametric equation that you can see right here in the middle. This dx dt becomes dx d theta, and dy dt becomes dy d theta. So we need to find the derivatives, square them, then add them together, then take the radical of them. In order to find the derivatives, we have to remember these relationships, that x is equal to r of theta cosine theta, and y is equal to r of theta sine of theta. Because they both depend on the independent variable theta, that means when we take the derivative, we have to apply the product rule. So this becomes derivative of the first times the second, and then minus the, or in this case, minus, because the derivative of cosine is negative sine times the first. So derivative of the second times the first. And we do a similar thing for dy d theta. We take the derivative of f of theta, which is r. So we could also think of that as r dr d theta times sine theta plus r of theta cosine of theta. So again, what we have here is actually dr d theta sine theta plus r of theta cosine of theta. And this represents dy d theta. And for dx d theta, we can write dr d theta cosine theta minus r of theta sine of theta. And this represents dx d theta. And then we're going to take these two and we're going to put them into the formula we had for the arc length of a parametric curve, which was dx dt squared plus dy dt squared under the radical. So dx dt is replaced by dx d theta, dy dt is replaced by dy d theta. And I've color-coded it so it's a little bit easier to follow because, well, we have to substitute these expressions that you see up here in place of the dx d theta and the dy d theta. So it's going to get a little complicated with the algebra. So the next thing we do is we substitute each of those values in there. So for dx d theta, we have r prime of theta cosine theta minus r of theta sine of theta, and we have to square it. So remember, when you square a binomial, you get three terms. You get the first one squared, the last one squared, and 2 times the product of the middle. So you get f prime of theta quantity squared, which is just dr d theta quantity squared, cosine squared, that's the first term squared, minus 2 times the product of the outside and the inside. So that gives us an f prime of theta, which is dr d theta, times f of theta, which again is r of theta, cosine theta sine theta, plus, and then we square the last one. It was negative, but when you square it, it becomes positive. So you get r of theta quantity squared times sine squared of theta. So remember again in all of these that f of theta is the same as r of theta. And f prime of theta is the same as r prime of theta, which is dr d theta. So it can be written in more than one way. We do the same process on the expression for dy d theta. This is very similar. It has a plus in the middle. It's r prime of theta sine theta plus r prime of theta cosine theta, quantity squared. So we get the first term squared, we get the last term squared, and 2 times the product of the middle. Now, what we need to notice, first off, is that this expression that you see here and this expression that you see here, those middle terms have the same value but opposite signs. So because one of them is -2 f prime theta, f theta, cosine theta, sine theta, and the other one's +2 f prime theta, f theta, cosine theta, sine theta, they cancel out. So they knock each other completely out and they're gone. So those two cancel. Now we're going to clean up the algebra a little bit so that we can see the next steps. So then we just kind of wrote down what was left. This came from the first terms of dx d theta squared, the last term of dx d theta squared, first term of dy d theta squared, last term of dy d theta squared, because the middle terms canceled each other. Now, in looking at this, what we want to do is we want to get both the ones with f prime of theta quantity squared together, and that's these two, so that we can factor out the f prime of theta quantity squared. So we're looking to factor out this because it is a common factor. Now, there's more than one way to do this, but this is probably the easiest way. And then we're looking over here at these two, and this is common for the second two. So we're going to break it apart. We're going to factor each individual one by pairing the first two and taking out f prime of theta quantity squared. And that gives us cosine squared plus sine squared. But we know what that is. It's a Pythagorean identity. It becomes 1. So we know that this is going to go away and just become the value of 1. Now, on the second one, we factor out the f of theta quantity squared. And again, we get sine squared plus cosine squared. So this second one is going to become 1 as well. That means that our integral, we started with the parametric equation, the square root of dx dt quantity squared plus dy dt quantity squared, where we replace t with theta to write it as a parametric. And we've simplified it down to this point, and we have f prime of theta quantity squared from here, plus f of theta quantity squared from here. And remember that f prime of theta is really dr d theta, so we have dr d theta quantity squared, and f of theta is really r of theta, so this is just r squared. Notice also that the limits of the integration, instead of going from t equal a to t equal b, we have angle variables. So this is from theta equal alpha to theta equal beta, which is pretty much the a to b for the for a parameter becomes alpha and beta when the parameter is an angle. Now, could you call them A and B? Yes, but we just typically use alpha, beta, and gamma for angle measures. So the typical way of writing this formula is to have the r squared first plus dr d theta quantity squared all under the radical. So I commuted the order of the two terms, and this is the formula that we have for arc length for a polar curve. And it is based on the formula of arc length for a parametric curve. It's essentially the same thing, but when we substituted, we got a lot of substitution and cancellation with the Pythagorean identity, and we ended up down here getting this integral. So now what we want to do is we want to apply this in example 1. So we're looking at this one. I believe this is a logarithmic spiral. So we're looking at this logarithmic spiral. E to the 3 theta is r. And I've only plotted from theta equals 0 to 2, something like that, because that's what it tells me to do. So what it's asking us to find is how long this part of this spiral is. Now, this spiral is very, very wide, and it gets even wider as it moves out, but it is moving in a spiral pattern going around like this, but the distance between the spirals gets larger as it goes out. Remember, the Archimedean, the distance between the spirals stays constant. In the logarithmic, it gets bigger as it goes further out. And this one is pretty big to start with. Notice we're out here a little bit past the radius equals 400 circles. So it's quite large. So we're going to expect that the arc length is going to be, well, bigger than 400, right? Because we've gone from the pole out past that circle, and it's not a straight line, it's curved. So it's got to be more than 400. All right, so what we want to do is we want to apply the formula that we derived up above for this equation, r equal e 3 theta, where theta goes from 0 to 2. And you can assume that the 0 to 2 is in radians, 0 radians to 2 radians. So again, from somewhere, you can tell up here, this is going from 0 radians around to 2 radians. 2 radians is in quadrant 2, where pi over 2 is about 1.57 and pi is about 3.14. So radian of 2 is closer to the pi over 2 position. All right, so let's take a look at the formula and let's figure out the two parts to the formula. Our equation is r equal e to the 3 theta. So we have r equal e to the 3 theta. So r squared is e to the 3 theta squared. And when you have one base and two powers, you multiply the powers, so you get e to the 6 theta. Now we need to know what dr d theta is. So I take dr d theta, which is the derivative of the exponential, which becomes e to the u times the derivative of u, and u is the 3 theta. So I get 3 e to the 3 theta, right? And my alpha is 0 and my beta is 2. And I'm going to put these in here. So I have e to the 6 theta plus, well, I haven't squared this one yet, so I could square this one here, or I can square it under the radical. A lot of students find it somewhat easier to do the squaring outside of the integral before they get started. Get some of the algebra done first. Just makes it a little bit easier. So we have 3e to the 3 theta quantity squared. 3 squared gives me 9. And we know e to the 3 theta squared is e to the 6 theta. So this gives me 9e to the 6 theta. And the differential is d theta. Now, I happen to know that e to the 6 theta is a common factor. You could factor it out, or you could just look at these and go, hey, those are like terms, right? I've got 1 here, 9 more. I must have 10 e to the 6 thetas. And in fact, that's exactly what we've got. So we've got the radical of 10 e to the 6 thetas d theta. Now I can split off the square root of 10 as a constant, and I can pull it outside. And then I need to take the square root of e to the 6 theta. So remember again that the square root is the 1/2 power. So I've pulled out the square root of 10. I still have the integral from 0 to 2. And I'm going to think of the square root of e to the, I'm thinking ahead. You should never think it right. Okay, so this gives me e to the 6 theta to the 1/2 power, d theta. I'm thinking of the square root as the 1/2 power, and half of 6 theta gets me back to 3 theta. So the final integral that I have to work with is radical 10, the integral from theta equals 0 to theta equal 2, e to the 3 theta d theta. Now this is a very straightforward integral to integrate. We want to do a u substitution. U is going to be 3 theta. So go ahead and pause the video, work out what the integral becomes, and turn the video back on. You will want to approximate your answer so we can tell how close to 400 it actually is. So let's see how you did. I made a complete switch out of theta into the substituted variable u. So I never go back to theta. You can, of course, go back to theta if you don't want to change the limits of integration, but it's usually less work to change the limits of integration. So I set u to be 3 theta. So du is 3 d theta. D theta is du over 3. When theta is 0, the lower limit of integration, u, which is 3 times theta, becomes 3 times 0, so it's still 0. And when theta equals 2, the upper limit of integration, 3 times 2 gives me 6. So I did a complete change of variables. I did a u substitution, and this gave me radical 10 from u equals 0 to u equals 6. I don't need to write the u equals, but I did that for you just to make it clear that I'm switching these limits of integration from theta values to u values. E to the u du over 3, so the over 3 comes out to join the square root of 10, e to the u from 0 to 6. And then, of course, you can substitute those values in. This is the exact value here, root 10 over 3 times e to the 6th minus 1, which is about 424.2. And again, that is very close to what we estimated it would have to be. Just looking at the image that we have up here, we saw that it was curving, that it was slightly longer than the radius equal 400. So we estimated that it would be over 400, but probably not by a whole lot, because while this does curve, it is roughly linear. Okay, so let's take a look now at the next example, which is example 2. Find the arc length of the polar curve r equals sine cubed of theta over 3. And this time they want us to go from theta equals 0 to pi over 2. Right? Now this one actually ends up being a rose shape, and we're getting part of the petal here. But the petals are really kind of small, right? So they're really rather small. So what we're going to do is we're going to apply the formula. You can tell that it's coming out from the pole here. When theta equals 0, the sign of 0 is 0, so it's at the pole. And as it extends to pi over 2, it kind of curves around a little bit into quadrant 1, and then it just barely crosses the pi over 2 line. So we want to apply our formula. So we have sine cubed of theta over 3, and here's our formula right here. So the first thing we're going to find is r squared. So r squared, if r is sine cubed, then r squared has to be sine to the 6th. The third to the second is 3 times 2, or the 6th power. So I get sine to the 6th of theta over 3. And then I need to find dr d theta. So I find dr d theta. Now this is going to invoke, and I'm probably going to need more room for this. Let's move this down. In order to find dr d theta, I'm going to have to invoke the chain rule, because I've got the 6th power applied to sine, and inside sine, I have a function of theta. So I've got nested functions here, the 6th power, the sine function, and the function theta over 3. So I'm going to find dr d theta. So this is going to pull the 3 to the front. I'm applying it here. That makes this sine squared of theta over 3. Then I have to take the derivative of the next layer down, which is sine. So the derivative of sine is cosine. Don't change the inside. And then I have to take the derivative of the inside. The derivative of theta over 3 is 1/3. Now I've got a 3 here, and I've got a 3 here in the denominator. So those are going to cancel. And this is going to give me sine squared of theta over 3 cosine of theta over 3. Now this is dr d theta, but the formula has dr d theta squared. So now I need to square dr d theta before I put it into the formula. Again, it does help to do some of the algebra ahead of time. These are both multiplied together, so I don't have to worry about FOIL or anything like that. It's not a binomial, it's a monomial. So I square each individual factor. So this gives me sine to the 4th of theta over 3 cosine squared of theta over 3. When you're squaring it, make sure that you're not also squaring the argument. That would be incorrect. It's sine raised to the 2nd power to the 2nd power, which is sine to the 4th, and cosine to the 1st to the 2nd, which is cosine squared. All right, now we're ready to go ahead and substitute it into our formula. So we're going to take a look at our formula. we have the arc length equal to the integral from theta equals 0 to theta equals pi over 2 of the square root of r squared, which we said was sine to the 6th of theta over 3, plus dr d theta quantity squared, which we said was sine to the 4th of theta over 3, cosine squared of theta over 3, all underneath the radical, and integrate with respect to theta. Now, again, in order to simplify the radical, we have to do something about this addition because we cannot split a radical across some ends. So we've got to do something so that they're only multiplied or divided. And the obvious thing is to take out a common factor. We do have a common factor of sine to the 4th of theta over 3. So we're going to take out the common factor of sine to the 4th. So we still have the integral from 0 to pi over 2. And this is going to give me sine to the 4th of theta over 3 times, taking 4 out of 6 leaves 2 behind, theta over 3. This takes out all of the sine to the 4th from the second term and just leaves plus cosine squared of theta over 3 d theta. However, this part right here is a Pythagorean identity. You know that sine squared of an argument plus cosine squared of the same argument must be 1. So this becomes a 1. So we just get the square root of sine to the 4th of theta over 3. Remember that the square root is the 1/2 power. So half of 4 gives us 2. So this becomes the integral from 0 to pi over 2 of sine squared of theta over 3 d theta. Now you have to go back and you have to remember how to do a trig integral. You've got sine squared, and the way we deal with that is with the double angle formula. And because it's sine, it's going to have a negative in the middle. So remember that the formula, and we have 0 to pi over 2 still, is going to be 1/2 the quantity, 1 minus the cosine of double whatever the argument is. So this is going to be 2 theta over 3 with respect to theta. All right, so hopefully that makes sense to you. The next thing that we want to do is we want to split this into 2 separate radicals. The first one will be able to be evaluated right away. The second one will need u substitution. So this is going to give me the integral from 0 to pi over 2 of 1/2 d theta. And the second one is going to give me a minus 1/2, the integral from 0 to pi over 2 of cosine of 2 theta over 3 d theta. And this, of course, becomes another u substitution integration problem, which I'm sure you can figure out. So go ahead and pause the video, work out the math, and then turn the video back on and let's compare our answers. So let's see how you did. When we're looking at this one, I made the substitution that u is 2 theta over 3, which gave me d theta is 3/2 du. I changed the limits of integration so I wouldn't have to go back to theta. So that changed the limits of integration. I was able to stick with u. That gave me a 3/2 inside of the d theta. So that becomes a minus 3/4. The integral of cosine is sine, evaluated between 0 and pi over 3. And when I simplify this and do the integration substitution, I end up with pi over 4 minus 3 root 3 over 8, which is about 0.136. So let's take a look back at our particular graph and see if we buy that value, if it looks like it's really that small. Well, yeah, it is pretty darn small. This is 0.5 to be right out here on this part right here. So that means this first circle is about 0.1, and it is past that circle, but nowhere near the 0.2 circle. So 0.136 sounds pretty reasonable. And that is what the arc length is. That's the measure of the length of that arc. So I think you'll find that doing arc length is actually pretty formulaic, as long as you can find r and you square it, find dr d theta, square that, add them together, then take the square root of the thing, make sure that you have the beginning angle and the ending angle, and that will give you the arc length. Now we want to switch gears and we want to talk about tangent lines. Now, tangent lines in some ways are more complicated. Finding dy dx, which is the slope of the tangent line in all cases, is not that simple in polar coordinate systems. The slope of the tangent line is always given as a vertical change over a horizontal change, rise over run, that's slope, right? So it's always dy over dx. So the problem is we're in r and theta. So we're going to have to compute dy dx using r and theta. So it's going to give us a formula. Now remember what we did before when we were developing the formula for arc length. We used the definitions that x equals r cosine of theta and y equal r sine of theta. And we applied the product rule for derivatives, and we came up with this formula that you see here. So we got dx d theta is basically dr d theta cosine theta minus r of theta sine of theta. And dy d theta is r prime of theta sine theta plus r of theta cosine theta. So we did this before. This is the same thing that we've done. And we can rewrite it instead of with f, we can rewrite it with r. And then we can also make a substitution that r prime is really dr d theta. So you get these two formulas right here, but they really represent exactly the same thing we see up there. Now, how are we going to get dy dx out of dx d theta and dy d theta? Again, we do this abusive notation. We take dy d theta and we divide by dx d theta. So it's sort of like the d thetas cancel and it gives us dy dx, which is what we're looking for. Now, that doesn't really make sense because we're doing operations. It's not really a fraction. It just turns out that it works and it gives us the right formula. So we take the ratio of the expression for dy d theta divided by the expression for dx d theta, and that will give us the slope of the tangent line. Now, remember, in order to write the equation of the tangent line, what we typically want to look for is y minus y1 equals slope x minus x1. So when we're looking at that, remember that this is all in rectangular coordinate systems. So this m that we got is in the rectangular system. It is dy dx. So we'll also need to come up with a y1 and an x1 at the particular point where we're finding the tangent line. And in order to find those values, we're again going to come back up here to our two definitions that x equals r cosine of theta and y equals r sine of theta. And we'll use those to find x1 and y1. Then we'll plug them into this point slope form of a line, and that will give us the tangent line. Now, it's a lot to remember. This formula is pretty confusing. I have had students memorize it, but the thing is, it probably won't stay with you. This idea probably will. Dy d theta divided by dx d theta probably will stay with you. And probably you have memorized already from trigonometry the relationship between r and y and the sine of theta. So you can get this formula by instead deriving it every time. So what I do is exactly that. What I do is I think of this as, oh, okay, what is y? Y is r cosine of theta, but r is a function. It's not a constant. So I have to do the product rule. So that gives me dr d theta cosine of theta minus r of theta sine of theta in the numerator. And then in the denominator, I do the same thing, but I write the expression for x. I think I may have these backwards. I think I've got these upside down. So I need to fix that in my notes. I should have them the other way around. All right, so coming up here, make sure I've got them right up here. Yeah, I do. X equals R cosine of theta, Y equals R sine of theta. That worried me a little bit. Okay, so this should be sine of theta, and this should be cosine of theta. So that's definitely something I'll have to switch in my notes. So you can derive it each time, all right? And this is what I actually do. I've just memorized that y is r sine theta and x is r cosine theta, and I apply the product rule. I've memorized the definitions of x and y, and I know that r is not a constant, so I know I have to use product rule. All right. Before we get into actually computing a tangent line, I thought it would be good to go ahead and review the finding the tangent line in a parametric equation, because it's similar to what we do with the polar equation. This is a particularly hard one, so I chose to start with this one. It's a good review of what we do with parametrics. We've got two equations, x equal 2 minus pi cosine of t, y equal 2t minus pi sine of t, and we're going from negative pi to pi. So this is called a prolate cycloid, and it looks like this graph. And we want to know the equations of the two tangent lines where it intersects itself. So in fact, this is at the point 2 comma 0, where it's intersecting the x-axis. So when we're looking at this, how can you know for sure that this is at 2, 0? I mean, how do you figure that out? So first off, let's talk about how you know. Now, we do know from what it says up here that it crosses itself at a point on the x-axis. So we know it's on the x-axis. So the first thing that we can say is y is 0 on the x-axis. And that's going to help us a lot to figure out what the actual point is and to figure out what value of t puts us there. Because if you look at the curve, it's probably graphing like this. It hits that point one time, then it curves around into quadrants 3 and 2, and then it comes back into quadrant 1, and it hits that point again. So it's hitting it twice at two different t values. And we need to know what those values of the parameter are. So we're going to use the fact that it's on the x-axis, so y has to be 0. So that means 0 equals 2t minus pi sine of t. That means that 2t is equal to pi sine of t. Now, this is not a simple equation to solve because we've got t inside of a trig function and outside the trig function. It makes this one quite difficult to solve. But what we can do is we can use Desmos or some other graphing utility to help us out. So what I did, you'll see right down here in this picture, is I graphed y equal 2x to represent y equal 2t. And then I graphed pi sine of x, or pi sine of t. And I looked for where they intersected. Where are these two graphs equal to each other? So in a sense, this one is the 2t, and this one is the pi sine of t. And I'm looking for where they're equal, where they cross, where they touch. And there are three places that Desmos tells us they touch. They touch at negative pi over 2, negative pi, at the origin 0, 0, and at pi over 2 pi. What we're interested in is, of course, the t value, which is negative pi over 2, 0, and pi over 2. So we have three candidates for where it is crossing that axis. So our candidates, this is true when t equal negative pi over 2, 0, and pi over 2. But keep in mind that this point back here between quadrants 2 and 3 is also on the x-axis. So y is also 0 here. So we need to make sure we're at this point, not this point. So now we need to verify that the x value is putting us over here to the right of the origin. So we're going to test each one of these in x. So we're going to find x of negative pi over 2. So what is x when t is negative pi over 2? And we get 2 minus pi cosine of negative pi over 2. The cosine of negative pi over 2, of course, gives us 0. And so this becomes 2. That is definitely one of the ones we're looking at. So that's probably maybe this one coming up from here. It's kind of hard to tell without actually putting on a slider bar and looking at it. So when we're looking at this one, we know that one of the parameter points we want is negative pi over 2. Let's check what we get when x is 0 or t is 0. So what is x of 0? Then we plug that in. We have 2 minus the pi of the cosine of 0. But the cosine of 0 is 1. And this gives me 2 minus pi. Now pi is about 3.14. So 2 minus pi is a negative number, about a negative 1.4, which is right here. So I can tell that that is this point over here, not the one I'm looking for. I'm looking for the other time it intersects on the right half of the quadrant plane. So when I'm looking at that, I'm suspecting it must be at pi over 2. And of course, it will be at pi over 2 because the cosine of pi over 2 is also 0. So we have pi times the cosine of pi over 2. This goes to 0, and we get 2, right? So that means that when the y value is 0, which happens when t is negative pi over 2, 0, or pi over 2, then the x value is either 2 or 2 minus pi. And the two we're interested in are the ones here. That's negative pi over 2 and pi over 2. Okay, now we need to figure out the equation of the tangent line. We have the point at which they intersect. That's our x1 and our y1. So we have our 2 and our 0. What we need now for the equations of the tangent line are the slopes of these lines that are tangent to the curve, but when it crosses at different points. So one of them you can see comes here, lays along as it comes across this part. And this one right here, the negatively sloped one, is as it comes out of quadrant 2 into 1 and then down into 4. So it's tangent at that point. So we need the equation of these two lines. And what we have so far is y minus 0 equals some slope x minus 2 on each one of them. Y minus 0, some slope x minus 2. Because of course they're at the same point. So now we need the slope. When we're looking for slope, we're always looking for dy dx. That's always going to be the slope of the tangent line, dy dx. But we're working in terms of x of t and y of t. So we're going to take dy dt and divide by dx dt. And we're going to evaluate it at two particular values of t, the negative pi over 2 and the pi over 2. And each one will give us a particular line. So again, what we want to do is find dy dx by finding dy dt and dividing by dx dt. I've gone ahead and done the work since this is mostly very calculations based. Again, dy dt is going to be the derivative with respect to t. So that gives us 2 minus pi cosine of t. And the derivative of x with respect to t, the derivative of 2 is going to be 0. And the derivative of cosine is negative sign, so we get a double negative. So that gives us pi sine of t. Now, this is a formula that will give us the value of the slope of the tangent line anywhere on that prolate cycloid, any point on that graph. I, however, am interested in 2 points, when t is negative pi over 2 and when t is pi over 2. So I took each of those two values and I plugged them into the formula that gives me dy dx, the slope of the tangent line. And I got negative 2 over pi when t is negative pi over 2. And I got 2 over pi when t is equal to pi over 2. So we have two slopes, negative 2 over pi and 2 over pi. So looking back up here at our equation, the one that is positive is the 2 over pi. And the one that is negative must be the negative 2 over pi. And again, you could drop the 0 and you could write this as 2 over pi quantity x minus 2 and y equal negative 2 over pi quantity x minus 2. You could write it both of those ways. I wouldn't take off if my students left the minus 0 there. I mean, it is point slope and you're making it clear that the y coordinate of that point is 0. So I would be okay with that. All right. Now that we've reviewed how to find the equation of a tangent line using a parametric, let's now apply the formula that we did before, and let's look at it for the polar curves. So remember, we have this elaborate formula, and I bet I've got this one wrong as well. I do. So I'm going to have to come back and fix this everywhere. So this is going to be sine of theta, and this is going to be cosine of theta. So I bet I've got everything completely upside down. Let's see if I actually did it right. dr d theta sine of theta plus r theta cosine of theta. Dr d theta sine of theta. Yeah, that's correct. So it looks like I just transposed those two when I was writing them out. My bad. I'll have to make sure I fix all of these in my notes. So I'll star this for myself. Okay, so let's take a look now and let's go ahead and find dy dx for this polar curve, r equal 2 cosine of theta when theta is pi over 3. And I do have a link to the Desmos graph of it. If you want to click there, you can click there if you have my notes. If not, you can pause the video, figure out what it is, and then type it in. You can come out there and you'll see this picture. So the graph basically of, what was it, 2 cosine of theta or theta over 3, I can't remember now what the equation was. Theta, r equal 2 cosine of theta. So when you're looking at that particular graph, it's a circle, right? So we have a circle out here, and we want to know what the equation of this tangent line is. But to write the equation of the tangent line, it has to be in rectangular coordinate system because the slope is a rectangular coordinate system measure. It's always dy dx. So we're looking at the particular point here when theta equals pi over 3. And this is our formula that we have right here. You can see this elaborate formula. Again, you can always derive it, take the derivative of r theta sine of theta, which is dr d theta sine theta plus r theta cosine theta, etc. Okay, so when we're looking at this, let's figure out the different parts. I need a dr d theta. So let's go ahead and find dr d theta. So I need dr d theta, which is going to be negative 2 sine of theta. Okay, so I've got dr d theta, a sine of theta, an r of theta, but this is r of theta, the 2 cosine of theta, and a cosine of theta, and the same pieces down here. We want to evaluate this specifically when theta is pi over 3. That's that particular point on the circle. So that, again, we know that pi over 3, if we plug it into r, the cosine of pi over 3 is a half, so the radius is 1. So this is actually at the point r of theta, which is equal to r of pi over 3, which equals 2 cosine of pi over 3, which is 2 times 1/2. And again, I'm trying not to skip any steps, is 1. So this is the ordered pair 1 comma pi over 3 in the polar coordinate system. We're going to have to figure out what it is in the rectangular system because we're going to need an x and a y for point slope form of the line. So we need to know what r of theta is at pi over 3. We figured out it's 1. That's going to replace the r of theta here and the r of theta here. Now we need to know what dr d theta is, again, at pi over 3. And I haven't computed that yet, so let's do that now. So dr d theta, when theta equals pi over 3, is equal to -2, the sine of pi over 3. And the sine of pi over 3 is the square root of 3 over 2. So I get -2 times the square root of 3 over 2. The 2's cancel, and I get negative the square root of 3. So everywhere I have dr d theta, I'm going to substitute the negative root 3. What I'm getting is dy dx evaluated at that one point. So I'm not getting a general formula this time. I'm getting the specific value. Could I get a general formula? Absolutely. Instead of plugging in the value, I would just keep them in their current form. So that would make this turn out to be dy dx is equal to dr d theta is -2 sine of theta times sine of theta, which would be sine squared of theta, plus r of theta, which is 2 cosine of theta, times the cosine of theta, which would give me cosine squared of theta, all divided by dr d theta is -2 sine of theta again, times cosine of theta. And then I've got minus r of theta, which is -2 cosine of theta times sine of theta. So the 2 in the bottom are like terms. They're both 2 sine theta, cosine thetas. I have 2 here and 2 here. They're both -2s. So it gives me a -4. All right. So I could actually write a formula for this. Notice that I've got a common factor of 2. You can factor it out, but they have opposite signs. So it's not going to become 1. It's actually a double angle formula, but it's fine just to leave it the way it is. All right. So then we have basically -2 sine squared of theta plus 2 cosine squared of theta, all divided by -4 sine theta cosine theta. Now, this is the formula that gives you the derivative anywhere on that graph. We specifically want it at pi over 3. So we're calculating the values at pi over 3, and we're going to substitute them into the formula. You can substitute them here, or you can substitute them here. It makes no difference. All right, you can do it in either location. So let me show you what it looks like if we do it directly. So I think we have just about everything we need except for the sine of theta and the cosine of theta. So let's come down here and we'll just write those down. Sine of pi over 3 is the square root of 3 over 2. And the cosine of pi over 3 is 1/2. All right, so now we have every piece that we need. So if I were plugging it in directly to find the specific slope at pi over 3, dr d theta at pi over 3, we said was negative square root of 3. So this becomes negative square root of 3. Sine of theta is square root of 3 over 2, plus r of theta is 1, and cosine of theta is 1/2 over. And again, dr d theta is negative square root of 3. Cosine of theta is 1/2 minus r of theta was 1. Sine of theta is square root of 3 over 2. All right, so now let's simplify this. Radical 3 times radical 3 becomes a 3. So this gives me -3/2 in the numerator, and I've really scrunched up my work here. Don't do this if you're my student. I will nail you to the wall for it. And then I've got 1 times 1/2, which is plus 1/2, all divided by, I've got negative square root of 3 over 2 minus another square root of 3 over 2. So that's -2 square roots of 3 over 2, or negative square root of 3. Which becomes -3/2 plus 1/2 is a -1. So I get -1 over negative square root of 3 which gives me 1 over the square root of 3, right? Now, what if I had stuck with the general formula for the derivative at any point? And if you're my student, I will ask you for this, and then I'll ask for it specifically at a point. You can either come back to here to plug in to find the point, or you can plug in here. It works in both locations. So let's go ahead and compute it at this point. So we'll say dy dx at theta equal pi over 3 is equal to -2 sine of pi over 3 is square root of 3 over 2, and it's squared according to our formula, plus 2 cosine of pi over 3 is 1/2, and it's squared according to our formula, over -4 sine of theta is square root of 3 over 2 times cosine theta is 1/2. Right? So let's simplify this and hopefully we get the same thing, or it messed up my formula somewhere, which is a distinct possibility. So when I square this, I get -2 times 3 over 4. When you square the square root of 3, you get 3, all right? And 2 squared is 4, plus 2 times 1/4. And here I've got 2 in the denominator times 2, which gives me 4, which will cancel that 4. So the denominator becomes negative the square root of 3. Now, what do I have in the numerator? The 2 and the 4 reduce, and this gives me -3/2. And the 2 times 1/4 reduces to 1/2 over negative square root of 3, which is the same thing I got before, -1 over negative radical 3, which is 1 over radical 3. So I know so far what the slope is, but I don't know the coordinates of the point. So this is a little different than what we saw in the previous one. So what I have so far is y minus y1 equal 1 over the square root of 3, x minus x1. I need to find the x value and the y value at that point. How do I do that? Well, I know how to do that. X is r cosine theta. And I know that r at that point is 1. And I know that the cosine of pi over 3 is 1/2. So this is at the coordinate 1/2. What is y at that point? Well, y is r sine of theta. R at pi over 3 is 1. And the sine of pi over 3 is the square root of 3 over 2. So I get the square root of 3 over 2. So my final equation for the tangent line at that particular point, I don't want to completely get the picture off, is going to be y minus the square root of 3 over 2 equal 1 over the square root of 3, x minus 1/2, right? And I would take that as the solution from my students, and hopefully your professor will as well, right? So what we've done is we found a couple of different things. We found a general formula for the derivative, the slope of the tangent line at any point. We also found it specifically at pi over 3, which turned out to be this 1 over the square root of 3. And then we used r at that specific point, which gave us 1, and the cosine and sine of the angle to find the x and y coordinates. So the tangent line equation, again, is written in rectangular coordinates, not polar, which can be a little confusing. Let's take a look at another example. Example 5, we have the equation of the tangent line to the polar curve at the point given. So we have 4 minus 3 sine of theta. This is a limacon. It's not a cardioid because these two aren't the same value. It's close, but it's not quite. So it's a limacon. It's a dimpled limacon. Remember, limacons can either be dimpled, have a flatter side than a true circle would, or they can have an inner loop. So there are 3 types of limacons, depending on the relative sizes of these two numbers right here. And we want to know what the slope of the tangent line and the equation of the tangent line is when theta equals pi. So theta equal pi, remember pi is around here, so it's coming out in this direction. So the first thing we need to figure out is, what is r at pi? Well, at pi, sine of pi is 0, so it becomes a 4. And you'll see this labeled here, 4 pi. So we know r is 4 when theta is pi. First thing we're going to do is we're going to go ahead and find the equation. And I bet my equation is wrong again. Oh, good. I didn't copy it down. Okay, so let's go ahead and find the equation of the tangent line. So what we're looking for is dy dx, which is going to be dy d theta over dx d theta. And this time I'm going to handwrite it so I know it'll be right. So this is going to be the derivative with respect to theta of r sine of theta without the equals. And this is the derivative with respect to theta of r cosine of theta. And then I apply the product rule because r is not a constant. It's a variable that depends on theta. So this is going to give me dr d theta sine theta plus r cosine of theta over dr d theta cosine of theta minus r sine of theta. All right, that's the formula. You can memorize the formula, but it's not going to stick with you. Better to memorize this form up here and then derive it by just applying the product rule every time. It's much, much better. Okay, so when we're looking at this formula right here, let's go ahead and plug in the pieces to get a generalized formula for the derivative at any point, and then we'll find it specifically at that point. So again, you can plug in at the beginning or at the end in order to find it at a specific point. It won't matter, it'll give you the same value. We're going to go ahead and find the general formula for the slope of the tangent line at any point. So dr d theta, I need to find dr d theta. So dr d theta, the derivative of 4 being a constant is going to be 0. Derivative of sine is cosine, so I get -3 cosine of theta. Everything else I have. So I have -3 cosine of theta times sine of theta plus r, which is 4 minus 3 sine of theta, but that whole thing is multiplied by cosine. So I need to put it in parentheses, all right? So this whole thing is multiplied by cosine, so I put it in parentheses since it has 2 terms. Then I'm going to divide by dr d theta, which again was -3 cosine of theta, multiplied by cosine again, so that's cosine squared, minus r, which is 4 minus 3 sine theta in parentheses again, multiplied by sine of theta, right? And we're getting the general formula for the slope at any point, all right? So this is going to give me, if I simplify a little bit, this is going to give me -3 cosine theta sine theta. Distributing the cosine theta here is going to give me another -3 cosine theta sine theta, which gives me a -6 of them, plus 4 cosine theta. That's my numerator, right? In the denominator, I have a -3 cosine squared of theta, and then I've got a -4 sine of theta, and then I've got a +3 sine squared of theta. Now, again, it's very tempting to want that 3 cosine squared, 3 sine squared to become the Pythagorean identity, but this one's -3 and that's +3. So it's actually a double angle formula. It is not the Pythagorean identity, right? So this is a general formula. We do not have a common factor between the numerator and the denominator, so we can't cancel anything. That's it. So now you have a choice. If you want to find the slope of the tangent line at that specific point when theta is pi, You can plug in those values here where you only need the cosine and sine of pi, or you can come back up here to this formula and you can figure out what dr d theta at pi is and what r at pi is, and you can plug in here. You should get exactly the same values. It should not make any difference. So no matter which way you do it, you should get the same result. So when we're looking at this particular one, we're looking at pi. So we have cosine of pi, which is -1, and sine of pi, which is 0. So our formula for dy dx, evaluated when theta equals pi, becomes -6. The cosine of pi is a -1, but the sine of pi is 0. So this term goes to 0. Then we have +4 times the cosine, which is -1. So this goes to -4 in the numerator. In the denominator, we have -3 times the cosine of pi, which is -1 squared. So that's going to be a +3. And then we have -4 times the sine of pi, which is 0. So this term goes to 0. And then we have +3 times sine squared with that 0 squared. So that term goes to 0. So we square the -1 to get +1. Did I say it's going to be +3? It's not going to be a +3. It'll be a -3 still. So I get -4 over -3, which is 4/3. All right. So what do I know so far? So far, I know that y minus y1 equals 4/3 x minus x1, right? I need my x1 and my y1. Now, you can pick it off of the graph, in fact, in this case, because it is exactly on the 4th concentric circle, which tells you it's 4 units to the left in the rectangular system, and that would give you a -4, and it's on the x-axis, so the y value is 0. So you could just get it directly from the graph, but we can also plug it in and find it. So this gives us y minus 0 equals 4/3 x minus a -4, which gives us y equals 4/3 x plus 4. All right. So let's talk about how to get it directly. Again, you're using the relationship. X is r cosine of theta, and you want to evaluate this when theta equals pi. And we said that r is 4, and the cosine of pi is -1, so we get -4. Y equal r sine of theta. If we evaluate y when theta equals pi, again, r is 4. The sine of pi is 0, so we get 0, which gives us the ordered pair -4, 0 for x1, y1. Right? And again, what we're looking for is this equation right here. We're looking for the equation of the tangent line. It will be in the rectangular system. I generally use point slope. Your instructor may insist that you put it into slope intercept, which I think is overkill, but they may insist. And if they do, then you would get 4/3 x plus 16/3. All right, we have one more example we want to look at, which is example 6. And this one says, find the equation of the tangent line to the polar curve at the pole. Now, this is the graph of r equal 2 cosine of 3 theta, which is a rose. And this rose has 3 petals. Remember, when the argument to the trig function is odd, it has that number of petals, and when it's even, it's double that number. So 2 theta has 4 petals, but 5 theta has 5, right? And the radius magnitude goes between -2 and 2. So the longest petal is 2 long. And you'll see that this is what it looks like. And the problem is the tangent line to the polar curve at the pole, well, it hits the pole numerous times. So let's start tracing. So it hits the pole here at this angle right here, and then it comes around at an angle of about pi over 6 and it hits the pole again at this angle, so the tangent line is positively sloped, then it curves around in quadrant 3 and it actually hits the pole again, but this time it's nearly vertical. So it's coming in like this, like from negative pi over 2 or something like that, depending on which direction you go. And then it's coming around like this again and coming back to here. So it's hitting the pole multiple times. Now we need to know over what interval it graphs the complete rows one time and one time only. We don't want it to retrace the curve. So it graphs completely between 0 and pi. So we're looking for the times when this hits the pole between 0 and pi. We're looking for those particular values. So how do we start? Well, when we're at the pole, the value of r is 0, right? We're at the pole. It's not extended from the pole at all. The pole, of course, is the origin, and r is 0 there. So we're basically looking for the points where this equation, 2 cosine of 3 theta, is equal to 0. So let's go ahead and solve that equation now. So when does 2 cosine of 3, oops, that's a 3, theta equal 0? So we can divide both sides by 2. That says the cosine of 3 theta equals 0. Remember that we are here between 0 and pi. So what values would cause it to be 0 when I get in there? Well, I don't know, all right? I don't know. But I do know that the cosine of pi over 2 is 0. So I'm going to start with one I know. I know that at pi over 2, it's definitely 0. And it also is going to be 0 at 3 pi over 2. So pi over 2 is here, and 3 pi over 2 is pi away from it. So at every multiple of pi, so plus n pi, every multiple of pi, I'm going to be at a place where the cosine is 0. So at pi over 2, and at 3 pi over 2, and at 5 pi over 2, etc. All right. So what I want to do is I want 3 theta to be equal to that. And this is coming from your trigonometry. It's probably been a while. You may not remember having done this. You did do this. So we've set 3 theta to be equal to a place where we know the cosine of that angle is 0. Now, how can I solve this for theta? Well, the first thing I do personally is I get a common denominator on the right because I want to have a common denominator before I divide by 3. So the first thing I'm going to do is I'm going to rewrite this as pi plus 2n pi divided by 2. I just rewrote this second term as 2n pi over 2 so I could put these in the same fraction. Then I want to divide by 3. So I've got 3 theta equal to this. It's the same as multiplying by 1/3. And that's going to put the 3 in the denominator over here and make it a 6. So theta needs to be somewhere, some value of pi plus 2n pi divided by 6. And this makes me feel pretty good because I could tell from the graph that this was coming in at an angle close to pi over 6. And I can tell by looking at this formula here that if I choose n to be 0, I'm going to get pi over 6. So what I'm looking for are values for this that fit within 0 to pi. Now, what could n be? Any integer value, any integer. So from negative infinity to positive infinity, but only the integers. So like -3, -2, -1, 0, 1, 2, 3, etc. Probably we won't need more than -3 to 3. So let's try it and see what happens. So I like to start at 0 because 0 usually puts me in the range I want to be in. And I know that just from experience. So if n equals 0, then I get theta equal to pi over 6 because 0 times 2 pi is 0, and I just get pi over 6. It reduces. All right. Is that in my interval? Yes, I'm looking for something that goes between 0 and pi. All right, that was the interval I was told. It graphs itself one time. All right, let's try n equal 1. I'm going to keep going until I get outside of the interval 0 to pi. So I'm going to go this way. So n equal 1, then I would get 2 pi up here plus pi, and that would give me 3 pi over 6. Which of course I know reduces to pi over 2, but 3 pi over 6 is definitely in my interval, so I keep going. All right, keep going until you get out of the interval, and I haven't left myself enough room here. N equal 2. So 2 times 2 is 4 pi. So 4 pi plus pi is 5 pi over 6, still in my interval. We should go one more, n equals 3. When n equals 3, I get 2 times 3 is 6 pi plus pi is 7 pi over 6. That is too large. That is not between 0 and pi because it's down here in quadrant 3. So it's past my interval from 0 to pi. Now let's test on the negative end because you could have one there. In this case, it's not likely, but you could. All right. We'll try n equal negative 1. When n is a negative 1, I get a negative 2. Pi minus 2 is a negative pi over 6. I'm already out of my interval because it's negative, it is below 0. So I'm already out of the interval, so I stop. Now, why did I say it's not likely? I knew I had found 3. I knew I'd found 3. I start at the pole. Let's start here. I don't know where it actually starts, but we'll start here. And it comes around. Let's count how many times it hits the pole. Once, twice, third time. So I'm anticipating that it's going to hit the pole 3 times, and I found 3 angles where that happens. So I've got 3 different tangent lines. I've got this one here where it looks like it's coming in at an angle of pi over 6. This one here where it looks like it's coming in at an angle of 5 pi over 6. And this one here, which must be the angle pi over 2. Right? So now what we want to do is we want to find the formula to give us the slope of the tangent line at any point. So we're going to go ahead and find dy dx. And remember that this is dy d theta over dx d theta, which is going to be the derivative with respect to theta of r sine of theta divided by the derivative with respect to theta of r cosine of theta. And then we can apply the product rule for derivatives. And this is going to give us dr d theta sine theta plus r cosine theta. And then in the denominator, we're going to have dr d theta cosine of theta minus r sine of theta, right? So we need to figure out what dr d theta is. We already have r. R is 2 cosine of 3 theta. So what is dr d theta? Well, dr d theta, we're going to have to apply the chain rule for derivatives because we have 2 functions, cosine, and the inside function is 3 theta. So derivative of cosine is negative sine. So we're going to have negative 2 sine frees the inside at 3 theta times the derivative of the inside, which is 3, which gives us negative 6 sine of 3 theta. Now putting this into the formula that we have up here, so we'll separate that part. So we have dy dx equal, and this is going to be dr d theta, which is negative 6 sine of 3 theta times the cosine or sine of theta plus r, which is 2 cosine of 3 theta, cosine of theta. Notice those do not have the same argument this time. All divided by dr d theta, which is -6 sine of 3 theta times cosine of theta. I somehow lost my bar there. Minus 2 cosine of 3 theta, that's r, times sine of theta, right? This is a general formula for the slope of the tangent line at any point on that rose. Anywhere on the rose, we can find the slope of the tangent line. All we need is the angle theta. Now, notice that this is a 3 theta and that's a theta, and that is going to affect the value, so you need to be careful. Now, we're looking for this at 3 different points, so we're going to have to plug in the 3 different values. So the first thing I'm going to do is I'm actually going to take a copy of this particular thing, and I'm going to write it down 3 different times, because we need to evaluate this at pi over 6, pi over 2, and 5 pi over 6. So go ahead and pause the video, work out what the derivative is, then turn the video back on, and we'll take a look and see what you got for your slopes of the tangent line at those angle values. Okay, so let's see how you did in your calculations. This is a pretty complicated problem because it intersects the pole 3 times. So we have to evaluate it at all 3 points. They're going to give us different slopes. You could tell that by looking at the tangent lines up in this picture right up here. You can see that the blue dashed tangent lines are clearly different. And this one is vertical. So don't be surprised when we get an undefined slope, since the slope of a vertical line is undefined. So again, when we're looking at this, what I did was I took theta to be pi over 6 first. 3 times pi over 6 is pi over 2, so that's 3 theta. And I substituted those into my general formula for the slope of the tangent line. And I worked out, of course, the cosine of pi over 2 goes to 0 in the second term in both the numerator and denominator. And it gives me -6 times 1/2 divided by -6 times root 3 over 2, which becomes 1 over the square root of 3. So what does that mean? That means when I have theta equal to pi over 6, the slope of the tangent line is 1 over the square root of 3. Now we know we're at the pole, and we know the value of x and y at the pole is just the origin, so it's 0, 0. So that means that this one right here, where I'm coming in at an angle of pi over 6, has the equation y equal 1 over radical 3 times x. And again, that's because it's y minus 0 and x minus 0, which of course just reduced to y and x. So we have that tangent line already. Now we want to find the other 2, so we need to evaluate at pi over 2 and 5 pi over 6. So I evaluated at pi over 2. So when I did pi over 2, 3 times that is 3 pi over 2. So I substituted that into my general formula for the slope of the tangent line. I got a lot of things going to 0 because the cosine of 3 pi over 2 and pi over 2 are both 0. And in fact, my entire denominator zeroed out. And I was left with -6 over 0, which is undefined, which just tells me it must be a vertical line. So this is when theta is equal to pi over 2. So looking at it, this is when it's coming in at this angle right here. So that's basically just the y-axis, which has equation x equals 0, all right? So it's the x coordinate of the point. That's the vertical line going through the origin. So that's the equation x equals 0. The last one we have to do is when we have 5 pi over 6. That's when it's coming around at this angle right here. You see it's coming around here. This is the 5 pi over 6 line. So it's coming in along that line. And we want to know what the equation of the tangent line is at that point. So when I did that, 5 pi over 6 is theta. 3 times that gives me 5 pi over 2. 5 pi over 2 is a 2 pi multiple of pi over 2. So it's basically back up at 90 degrees again. So when I plugged those values in, I got some cancellation in the second terms of the numerator and denominator. They zeroed out because the cosine of 5 pi over 2, like the cosine of pi over 2, is 0. And when I simplified this, I got negative 1 over the square root of 3. So there's a kind of symmetry going on where one had a positive 1 over the square root of 3, and the other slope is a negative 1 over the square root of 3. So again, coming back up here to our graph, we can tell that that's this equation right here. This is y equal to negative 1 over the square root of 3 times x. And again, that's because it goes through the origin where the point is 0, 0. So I hope this makes sense to you and that you've enjoyed learning about arc length and finding the equation of a tangent line in polar coordinates. In our next video, we're going to take a look at finding area with polar graphs. So for example, looking at the rows right here, we want to know how much area is inside one petal, or maybe how much area is inside 2 petals, or maybe all 3 petals. How much area is inside those shapes? It'd be very difficult to do with the rectangular system, but you're going to find that the formula in the polar system is quite easy. I hope to see you there.